So welcome to lecture 5, and we will start chapter 2, isn't it? Book, which is also called Kinematics of Deformation. So we got accustomed with several terminology till now, and we are going to start with kinematics of deformation. So by kinematics, it means we are going to talk about variables which will be used to describe geometry of deformation for a continuum body. Okay, so we are going to talk about variables to describe geometry and so say also motion of deformation. So this is done without bothering about who is causing this deformation. So that is called kinematics. When you talk of the motion or the deformation without bothering about why such a motion or deformation is occurring, that is kinematics. Okay. Okay, so I'm not going to use green color. All right, so, and I'll just write here that the following week we are going to have a quiz. So that's quiz 1 based on lectures 1 to 6 of AML 805, I guess. I forgot the name of the course, but okay, I can write advanced theory of elasticity. So this is going to be coming Saturday or Sunday. Okay, AML at 41. All right, so let's begin the course now. So you see, in kinematics, when you talk of kinematics of deformation, we have to think of the reference configuration, which is getting mapped into the deformed configuration, okay, or the current configuration. And any point in the reference configuration, the material particle, so to every material particle, as we have seen, there's a unique position which is given by x, and that point goes to y in the current configuration, right? That's how we denote it. And these x and y would be measured relative to some point O, which could be the origin of a coordinate system or any other arbitrary set point. Okay, usually it's the origin of a coordinate system. So this becomes the position vector of x, and this is of y. Okay, and we know that this mapping is given by the deformation map, which we denote by y hat, right? The hats are used to imply that it's a Lagrangian function. That's why you see that the argument depends on x, the position in the reference configuration. Okay, we have already seen this. All right, and therefore you can also think of the displacement, no? So displacement also you can think of change from the reference configuration, and this red line is your displacement u, isn't it? And u, the function you had, for example, of x is simply y hat of x minus x, isn't it? I hope there is no question till now. Okay. And then we also saw that this is a one-to-one map. This y hat is a one-to-one map to every particle in the reference configuration. There is a unique position in the deformed configuration. Okay. So therefore, we can also think of an inverse function, which goes opposite way, like this, and that we denoted by y inverse, no? But you see this inverse, okay, we can write either as y hat inverse, or we can think of a function x with a bar, because the functions with a bar are used to denote Eulerian functions, isn't it? So basically, this implies your little x is then equal to this function with a bar, and it takes y as the argument. Okay, so that's the inverse function, and it's one to one. Therefore, such an inverse function exists, right? This also implies that, for example, I can write that this function, inverse function, okay, if you pass to it this particular argument, can you guess what you will get? Anyone? That's right. What you get is x itself. So you can see that there's an inverse function and then a direct function which are composed. Therefore, it becomes an identity function. So whatever you pass to it, you get back the same thing. Okay. So this composite map is actually identity function. And sometimes this composite map is also written like this: x with a circle. Okay. So this is the composite map, and because of them being inverse of each other, it's also an identity function, identity map, right? Likewise, you can also think of an opposite sequence composition, y hat of x bar, right? And you pass to it y, and what you get back is y itself, right? So this is also a composite map, which is again an identity map. Okay. All right. So having seen this, um, we also should see that although we are writing vectorially, but to these vector functions, you see, it's a vector function because it has to give three. It is returning a vector, and the vectors will have components in a coordinate system, right? So suppose your y is yiei. Okay, so this is just, you are just decomposing this vector in this coordinate system of e1, e2, e3. Okay, so basically this is what it means. If you follow my notes, this is how I write. So a vector is a vector, but its representation, we denote it with this square bracket, and we have to say in what coordinate system you want to represent. So that's then y1, y2, y3. Okay, the three components. And if it is like this, yi hat, ei hat, where the hats are different coordinate system. Okay, so in that case, I will say that the same vector, its representation, and in at a subscript will say what coordinate system I want to represent it in. Then in the hat coordinate system, it will look like this. It's different, right? So you can see that the representation, the two representation of the same vector y are different because they belong to different coordinate system, right? So this you should always understand that although it's the same vector, but its representation, or we say its column form, depends on the coordinate system. The vector itself is invariant. Okay, vector itself does not change if you change the coordinate system, but its representation changes. So this is something all of you have to understand very, very, well. So I hope none of you have this any doubt on this. So having seen this, now if we want to represent these vectors, let us say in E1, E2, E3 coordinate system, then I would say that to this y hat function, we have then yi hats, which gives the three components of the vector y1 hat, y2 hat, and y3 hat. Okay, and likewise for every position x, we have its three components x1, x2, x3. And we have to understand that these component functions, for example, y1 hat, which is returning y1, depends on not just one component x1. So that is not true. Okay, it depends on all the three components, and we'll see today examples of it. So this is not true. This is true. So each of the component functions depend on all the three components. So we can say that yi hats, they depend on all the three components. All right. So having seen that this is the deformation map, and we'll also see some examples of it as we go down, There is also this concept of what is called deformation gradient tensor. Okay, so what is this? This is simply the gradient of the deformation map. I can write here, as the name suggests, it's the gradient of the deformation map. And which gradient? You can recall from the previous class, there are two types of gradients, Lagrangian gradient and Eulerian gradient, right? And the deformation map depends on x. So we have to take the gradient with respect to x. So therefore it's Lagrangian gradient. So we can write it as, no, this gradient, and you can say here it's x, and I have to do it for y hat. Okay, and the same thing you can recall, we would write it with a big G, grad of y hat. Okay, and it is in short it is written as big F, and since it's a second order tensor, it comes with two tildes. Okay, and it depends on the Lagrangian position x. Okay, so this is basically a second order tensor. You know that gradient increases the order of a tensor, right? So it's just the abstract form, but there is also a formula for gradient of any tensor. The way it is done is the following. So gradient of a tensor, which could be first order, second order, third order, fourth order, anything. So gradient, let us say with respect to Lagrangian gradient, so x of a tensor denoted by the circle. So this is, by definition, it is del over del xi of this circle, and then you do tensor product with ei. Okay, it's just a definition, and you could also write it as del over del x j of that circle, and then tensor product with ej, right? Because you see it's a dummy index, so you can replace I with j also. Okay, now when we think of this gradient of y hat, so this big F is therefore, what is that going to be? So big F is then by definition del over del x j, let us say, of this circle, which is y hat here. Okay, and then you do it with respect to, sorry, this tensor product ej. I hope that all of you are following this tensor product. You are all aware, no, what is this tensor product? Anybody not aware about tensor product? Please write no if you don't know. Hasn't this been taught in the math class, the tensor product? See, so therefore you had to read my lecture notes. You haven't read it yet. So anyway, I'll do it here. You see, when you have two vectors A and B, you have two vectors A and B, there are so many operations you can do with this vector. So one of them is very well known, it is dot product, A dot B, right? And you know that if you want to do it in component, it is AIBI, isn't it? Just take the product of the individual components and sum it. And if you want to write it in a matrix form, then it's the column form of A, which will have the three components, and take the transpose of it and then multiply with the column form of B. Okay? So you see, since you are taking transpose, it becomes like this. And then you multiply with B. So this is basically A1, A2, A3 times B1, B2, B3. Okay, and when you multiply, you indeed see that it is AIBI. Okay, that's the dot product. Then you also have cross product, right? And cross product is also called vector product. And dot product is also called scalar product. So this is dot product slash scalar product. Okay, whereas this thing is cross product slash vector product. And there is this third one which is called tensor product, A tensor product B. See, scalar product is reducing the order of the vectors. It is making it scalar. Vector product keeps the order the same. Whereas this tensor product, this increases the order. Okay? And how, if you want to denote this in, let us say this is equal to C, then, in the matrix form, or if you want to represent it, second order tensor is going to become a matrix, and it is the column of the first times column of the second, but now the second one is transposed. You see, in the dot product, first one was transposed, but here you see dot product first one is transposed, but here in the tensor product second one is transposed. It's only then that you can get a matrix from here, no? So this means you have A multiplied with B transpose, and what you get is then indeed a matrix whose ij component is simply AI into Bj, right? So basically Cij is AI times Bj. Okay, so that's the meaning of tensor product. We can also think of it as follows. So this C is A tensor product B. So it is, you can write AI EI tensor product Bj EJ, and then scalars you can move AI Bj, and it is an EI tensor product EJ. Okay, so this is a special form of tensor, which is also called rank 1 tensor. So you can see this coefficient of EI tensor product EJ are actually the components of the tensor C. Okay, and that's the ij component. So Cij is basically ai bj for this spatial tensor. But in general, a tensor C will be such that it is Cij ei tensor product ej. Okay, you can relate it with a vector v, but when I write it as vi ei. So what is this? When you do it, you are basically expressing this vector v in E1, E2, E3 coordinate system, and then vi's are the components, right? So E1, E2, E3 are the basis of the vector. So for the second order tensor, this thing is the basis, and Cij is the component of this tensor along the basis Ei tensor product Ej. Okay, so if I write here, so Cij is the component of tensor C along the basis Ei tensor product Ej. Okay, there are many more things that I have taught in that class, and you have to go and look it there. Professor Arga Samantha is also teaching. So and so ensure that all of you are reading. That's why I'm taking the quiz. So anyway, this was a brief detour of second order tensors. Now coming back here to the deformation gradient tensor. Now you see this is I want to get the gradient of this vector y, vector function y. So I can also write it as del over del xj times y hat I ei, isn't it? Just decomposing this vector function, tensor product ej, and therefore what you get is del yi hat over del xj times ei tensor product ej. See, we did not differentiate ei with respect to xj because E1, E2, E3, so this basis is constant, no? It is not changing with x1, x2, x3. Therefore, we did not differentiate. But if you choose a basis which is also changing, for example, in cylindrical coordinate system, ER, E theta, EZ, ER and E theta change with theta. So in that case, if you take differentiation with theta, ER and E theta, you'll also have to differentiate it. But here, you don't have to do that because you have the basis, the very simple Cartesian basis, E1, E2, E3. Okay. So somebody is asking, what is basis, sir? So I think you have to see, this must have been taught in the math class. And please read my notes or my lectures. Look at the video lecture, not just the lecture notes of AML 841. You'll understand all of these things. Anyway, so this is your F, and if you write it as, Fij Ei tensor product Ej, then you can very easily correlate and see that Fij is actually del yi hat over del xj, isn't it? So that's the component of the deformation gradient tensor. And this component is in the E1, E2, E3 coordinate system, okay? Anyway, so proceeding further, So having introduced this deformation gradient, let's now see where it is, what is its physical significance. So we are coming now to the physical significance of this deformation gradient. So this was just a mathematical thing, but let's talk about the physical significance. So, okay, I think I have to go down. All right, maybe I can use this space. So again, you have this reference and deformed configuration. So let me make this a bit different. So this is reference and this is deformed configuration. And think of a point P here, which is at the location X. Okay. And another point, I mean, the same point here is denoted by, let us say, P prime, and it's at the location Y. Okay. Now, as of now, it is just a point, isn't it? But let's now think of a line passing through the point P. A material line, basically. It's not a line in the space, it's a material line. That means it contains particles of this body. And suppose that this line has got P and Q as the two ends. Okay. So this Q has position as X plus, let us say, delta X. Okay, so delta X being the vector from P to Q. Okay. So where will this Q go in the deformed configuration? So in the deformed configuration, it may have come here. And we can say it has come to Y plus delta Y. All right. And since it's a material line, so that's Q prime basically. But notice that it's a material line. So it's very important to understand this. So this is a material line. So can you guess what will happen to this line in the deformed configuration? For a general deformation, how is this going to look like? Will it remain a straight line? So it is straight. Will it remain straight? Zigzag, warped, curved? Yeah, so your guess is correct. It's going to look like a curved line, maybe something like this, isn't it? Depending on how complex is the deformation, it need not be a straight line. That is for sure. Okay. But think of this delta x. So what happens if delta x is taken to be very, very small? Then in the deformed configuration, again the line joining P and Q will be curved, but you see, you are basically, so suppose I, bring this Q close to P. Okay, I'm bringing this Q close to P. So as you do that, you will also come close to P prime. From Q prime, you start traversing along this curved line, and you are starting to get close to P prime, isn't it? So in the limit, when delta x becomes really, really small, or what one says is infinitesimal, what's going to happen? That curved line, isn't it that you can approximate it as a straight line? Isn't it? You can very well approximate that as a straight line. So it's an approximation. So this is what I'm going to draw next. So you have again those two bodies, and you have P, which becomes P prime here. So although I'm drawing here a finite length line, but it's supposed to denote a very, very small line. Okay. So this is x, this is x plus delta x. Now delta x is very small, or I can say it is infinitesimal. So in that case, the point y will go to, it will look like a straight line, isn't it? And this is y plus delta y. So now the question is, can we relate delta x and delta y? So you see, delta x is a material line, infinitesimal material line, and we want to know how has that transformed to delta y. Is there a function that can be used to relate these two? So that's the question. Is there a function that relates a material line in the two configurations? So let's try to explore that. So maybe, we can um, start with the deformation map itself. So you can say that x plus delta x, sorry, y plus delta, I'm sorry, the the other point y plus delta y is actually this function y hat of x plus delta x, isn't it? So there's nothing wrong here, right? And if you, for example, write this in component form, so then you have yi plus delta yi, the ith component, okay, along the ith coordinate system. So that's going to be equal to this yi hat, right, the ith component function. And what you have here is, I won't use I again, I have to use, let us say, j, xj plus delta xj, right? And remember that this j goes from 1 to 3. Or if I have to be more explicit, I could write it as x1 plus delta x1, comma x2 plus delta x2, comma x3 plus delta x3, isn't it? I think there is no ambiguity as far as this is concerned. Now, because this delta x1, delta x2, delta x3 are very, very small, we can do Taylor's expansion, right? We can do Taylor's expansion of this function y hat about the original point x1, x2, x3, right? About the original point x. So when you do that, you see it's a function of three variables. So you'll have to do Taylor's expansion in all the three components. And I think all of you already know this. So this is going to be yi hat at x1, x2, x3, right? Plus del yi hat over del x1 multiplied with, and you see this derivative is also evaluated at x1, x2, x3. And this has to be multiplied with the change in the x1 coordinate, which is simply delta x1, right? Then you have other one, del yi hat over del x2 into delta x2 plus del yi hat over del x3 into delta x3. Okay, so now I'm going to use summation convention, for example. So this is simply yi hat, and in the argument you have the vector x, no? x1, x2, x3 means the vector x, plus del yi hat over del xj evaluated at the vector x. You see the derivative has to be evaluated at the vector x multiplied with delta xj, isn't it? And you see the Taylor series, it actually runs to infinity. But what are those extra terms? They are quadratic in delta x, isn't it? It will have delta x1, sorry, delta x1 square, delta x2 square, delta x3 square, or delta x1, delta x2, delta x1, delta x3, delta x2, delta x3, isn't it? So those are the higher order terms, which we denote it with the symbol big O. And since it's a square, I could write it as delta x whole square. What is this thing with a with a vertical thing? So this is the magnitude of delta x. So this thing over here, that's the magnitude of delta x, which is delta x1 square plus delta x2 square plus delta x3 square, which is also called norm. Yeah. So two bars are used to denote norm. So all this is there in my notes if you go there. Okay, now something more. Um, so this is right now in component form. Can we switch back to vector form or say tensor form? So this is for each of the components, right? So if I write all the three components together, this is y1 plus delta y1, y2 plus delta y2, y3 plus delta y3. So that's equal to this y1 hat, y2 hat, y3 hat, isn't it? Plus, you see what is going to come here? you'll have a matrix of del yi hat over del xj multiplied with delta x1, delta x2, delta x3, isn't it? So I have just written all the three components together here, plus this higher order term. Okay. So um, now do you see that? I mean, this you can also write it as, if I want to switch back to tensor. See, this is the component, but if you allow me to switch back to tensor, can I write it as y plus delta y? That's equal to this function y hat of x plus, you see what is this? This matrix del yi hat by del xj. Isn't this your deformation gradient tensor? So this matrix is the um, representation of that second order tensor, which is deformation gradient, right? So I could write it as big F at x multiplied with delta x. You see, matrix times this vector. So that's what I wrote here. Second order tensor multiplied with delta x. Okay? And plus this remaining term of the Taylor series. And then you see this small y is actually the map of x, no? So aren't these two going to cancel? Right? Because this small y is actually the map of x. So it should be equal to y hat of x. So this brings us to this following formula, that delta y, the deformed line element, is equal to the deformation gradient tensor multiplied with delta x, the undeformed line element, plus this extra term. Okay. Now this holds for a finite delta x. But as we saw, so we have to now take the limit. The magnitude of delta x going to 0. So in that limit, what is going to happen? The delta y's, of course, they become very, very small, no? So you can say that it becomes dy, right? That's equal to big F into dx, isn't it? And this thing, you can drop it, isn't it? You neglect that? It's really, really small, no? Suppose this delta x is zero point 0.1, then its square is 0.01. But I'm not talking of zero point 0.1. You have to take the limit going to 0. So suppose it is 10 to the power minus 4. Then the square is 10 to the power minus 8. So you can see there is so much of difference. If it becomes 10 to the power minus 8, if delta x is 10 to the power minus 8, then its square is 10 to the power minus 16. Right? So compared to delta x, you can neglect the quadratic component, quadratic and the higher orders, everything. So this O delta x square contains all of them. When I say delta x square here, it also has cubic, fortric, all of them. So they all can be neglected in this limit. And so this is what you derive finally, that infinitesimal line elements in the two configurations are related through the deformation gradient, big F, isn't it? So this is the thing which holds for arbitrary deformation. Arbitrary deformation. So let me now again draw the picture. So reference to deformed, and suppose you are at a point X, then think of very, very small lines emanating from X, tiny lines. So these are your dx, right? These are your dx. And then you come back here at y, then you again have those tiny lines. And what it says is that those tiny lines are simply related through this big F. So the tiny lines dy is equal to big F of dx. So this is, and this big F is different at different x. You see, this big F, it's a function of x. So at this point, you have one big F. At another point, suppose it's here. So this is, let us say, x1, and this is y1. So what you have here is dy is equal to f1 of dx1. Okay, so this is relating, say, these two. But for another point, let us say this one, which is the point x2, and here is a point y2. Then again, you have those tiny lines here, material lines. Okay, these are not spatial lines, material lines engraved in the body. So these are getting rated through f2, whereas f2 is simply evaluated at x2. Okay, so what you see is that if you want to relate the tiny lines, you just compute the deformation gradient at that point and simply relate it. Any question? Okay, I'm already crossing the time. I wanted to do examples also, but I guess I have to wait until the next class to work out the example. Okay, so let's continue from here in the next class. But if you have any question, please ask me.
Sir, how y and y cap cancel out? This is
How,
Abhishek.
why can?
Y cap cancel out.
Okay. Um, See, look at the original picture. So this y, point y here, is the map of x, no? Right? So isn't this y equal to y cap of x? So when you wrote this thing here, you also have y equal to y cap of x, right? So therefore I could cancel them. Y is equal to y cap of x. Okay, any other question?
But sir, in previous lecture you told y cap is mapping from x to y,
Yes.
and y is mapping from o to y. Then how it's equal?
Y is a mapping from O to Y.
Uh, o means particle to y, actual body in actual body.
Well, but didn't I also say that this Y, so I think what you're saying is that Y is equal to this map
Yes,
configuration
yes, yes, sir.
I of some particle p,
Yes, sir.
right?
Yes.
And then this x is the configuration map xi ref
Yeah, JRF.
p.
Yes, sir.
But recall that these two also induce another map that we are talking about here, y hat,
Yes, sir.
which is directly relating y and x,
Yes, sir.
right? And this is what I have done here.
Okay.
Yeah. So now I'm forgetting about this body, the mathematical abstract body B, and directly working with reference and deformed configuration. So we are not bothered about this configuration xi anymore. We are just bothered about this y hat, the deformation map. Yeah,
In gradient of a tensor, you
yeah.
used the similarity sign instead of equal to sign. Is there any particular reason for it?
Let's see. Where you are saying this thing?
While explaining the tensor product.
You mean here? This is this what you're saying?
Ah, yes, sir.
Or you mean here, this three thing?
Yes, yes.
See, whenever I write these three things, no, it means you are defining it like this. That's a definition. And that definition, many at many places you will see they also write it like this. But in the next class, we are going to start with examples. Okay. So we'll take several examples of this deformation map corresponding to, let us say, stretching of a body, shearing of a body, bending of a body, and you will see how exactly the formula looks like. That function y hat, or the components y1 hat, y2 hat, y3 hat. How does it look like for some physical deformations? Okay, so Sanchita is asking, if we already have deformation map, then why we need u? Well, because you mean displacement, right? So, of course, you can extract one from the other. So, you don't need both of them simultaneously. You can extract one from the other. So, I hope that is answering your question, Sanchita.